and 0. But maybe there's some complex thing, or maybe some abstraction in some like some book million years. I don't know. But yeah, you understand from the second part. Okay. Injection. Okay. To prove injection, you do this. Suppose f of x equals f of y. Then e to the x by definition equals e to the y. Then it's very simple. Take natural logs of both sides. And what is this equal to? X equals y. Very simple. There you go. All right. So this function is a bijection. So now I'm going to do the difficult one. So I was thinking about doing countability and setting up the Cartesian plane, looking at diagonals. I don't want to do that today because I don't want the idea to be countability today. I want to go straight to isomorphism as soon as possible. But one of the things, there's an alternative proof to proving the rationals are countable, and there's a big step in it that I really liked. And because we studied number theory together, I want you guys to see this step. So, okay. So, all right. And this doesn't prove it for all rationals, but the remaining case is just so simple. It proves it eliminates the big guy, eliminates the big case, then only little case left. It's like eliminating Dr. Evil, and then little mini me left. This is all we're doing. So we're proving there's a bijection between. By the way, you can read this on your own. I'll teach it probably another time. Very easy. If there's a bijection between two sets, then there's an inverse. There's a way to go back. I'll make it more formal next. When I run into it, I will make it more formal. If there's a bijection between, even though that's an important property, inverse. Between S and Q2, where S equals the set of natural numbers with at least one prime divisor of odd power and at least one prime divisor, or actually even power, one prime divisor of odd power. And this is a big N. I saw the proof online and I had a problem. So N, all odd powers are greater than or equal to 3. Okay, that's S. Q2 is much simpler. So Q2 equals the set of all rationals so all rationals where m over n, where they're in reduced form, there's common divisor of m, n equals 1. And lastly, we want it to be an m, n is greater than equal to 2. So whenever you see greater than equal to 2, think about the fundamental theorem of arithmetic. Okay. So, all right, let's prove the bijection. Okay. So, so define f. So take f. Okay. So I so define, so for any natural number of that form. Okay. So take a function f of n, and remember any n can be written in this form. My fundamental theorem of arithmetic, I can write it as p1, but it's going to, let's go to even and odd powers. n1, p2, n2, of the ps, ns, times q1, or actually evens, times q1, n1, 2n1 plus 1, times q2, 2, or actually, let's start a different m1, yeah, times 2m2 plus 1, up to q, r, 2mr plus 1. So all I did was I just separated even and odd powers. Not a rocket science. All this is fundamental theorem of arithmetic applied to natural numbers greater than or equal to 2, and just take the even powers here and odd powers there. These are distinct forms, by the way. Okay, and this guy equals, very simple. Alright. I put the powers on the p1s on the top, but I separate between even and odd powers, right? I put the even ones, primes with the prime divisors of even powers on top. And I move the 2's, I make it n1s, n2s, up to this ns. I took them here, put them on top. The ones corresponding to even powers, right? And here's the thing, each of these n1, n2, n3, because they're divisors, they have to be at least 1. So p1 raised to n1, at least 1, p1 raised at least to a power that is raised to 1, right? n1 has to be greater than or equal to 1. But it can be any number here, any positive integer. So that explains the first proviso. Second proviso, so here, the odd powers, they now go on denominator. But you replace the 2m1 plus 1 and make them into m1s. So q2, m2, qr, mr. So here's the thing. I made the proviso that all odd primes are greater than or equal to 3. Well, if we know it's greater than or equal to 3, then all these m1s up to mr have to be greater than or equal to 1. So we're still good. We have not run into anything bad yet. The reason why I'm doing this is because I want to prove it's bijection. If you had things raised to 0 equal 1, that's bad. Bad things happen. Don't do that. Because then we lose surjectivity. Because, 1. There's many ways to get 1. Raise things to 0 power. Raise anything to 0 power. You got 1. Okay. Hopefully you get that. Okay. So the first part is I want to prove it's surjective. Okay. So let x. Can you see that? I don't know if you guys see that. Let me rewrite this. Up. The P and S up to Q1 up to QR and R for MR and 1 up to MR. Okay, very simple to prove it's surjective. It was just a cool idea. Okay, Q2. Okay, so let m over n be in. Maybe I should go back to this part. Okay. Okay, you're gonna have to rewind to get S again. But Q2 I want S has a little bit of provisos in it, but I already used the proviso really now. Okay. So let m comma n be in Q2. Okay. So it's in Q2. So by definition of Q2, there is common divisor of m comma